Today I'll be discussing about water. So we'll be talking about safe and wholesome water, the sanitary sources of water, the water purification processes, water quality standards, concepts of water conservation and rainwater harvesting. So the study of disease is really the study of man and his environment. As you all know, the epidemiological triad consists of agent, host and environment. So environment is very important in the causation of disease and in maintaining the state of health of an individual. All the external factors, living and non-living, material and non-material, which surround man are a part of the environment. Environment can be physical, biological or social. What is sanitation? The science of safeguarding health is sanitation. It is a way of life. It is the quality of living which is expressed in the clean home, the clean farm, the clean neighborhood and the clean community. And the whole field of controlling the environment with a view to prevent disease and promote health is known as sanitation. Environmental sanitation is defined by WHO as the control of all those factors in man's physical environment which exercise or may exercise a deleterious effect on his physical development, health and survival. And water forms a very important part of environment. Adequate supply of safe water and basic sanitation is one of the essential components of primary health care. So what is safe water? Water that is free from pathogenic agents, water that is free from harmful chemical substances, water which is pleasant to taste, that is, it is free from odor and color, water which is usable for domestic purposes, and the appearance, taste, and odor of the drinking water is acceptable to the consumer. Then potable water or wholesome water. This is safe water, which is pleasant to taste, it is odorless, it is cool and it is colorless, and it does not stain the clothes or the utensils. Now, water has various uses. It can have domestic uses, then uses for public purposes, it can have industrial uses, uses for agriculture purposes, uses for power production and other uses. Then we have certain norms to calculate the water requirement, which are calculated per capita per day. So in our country, it has been estimated that in rural areas, the minimum requirement of water per capita, means per person per day, is 40 liters and it can vary up to 55 liters. Whereas for every head of cattle, the water requirement is calculated at 30 liters per head of cattle per day. In urban areas, in towns with piped water supply without sewerage, the requirement norm is 70 liters per capita per day. Cities with piped water supply and existing or planned sewerage system, 135 liters per capita per day. And metropolitan or megacities with piped water supply and sewerage, it's 150 liters per capita per day. So you see, water exists in various forms as ice and snow. Then there is surface runoff. It infiltrates and percolates into the soil. And then there is a water table below the soil in the subsoil. Then there is flow of groundwater into streams and rivers and ultimately into oceans. Water evaporates from there, then clouds are formed and again rainfall occurs and the water, again the cycle continues. The water resources or the water reservoirs are distributed as that the ice caps and the glaciers, they have 1.7 to 2.02% of the water on earth. The soil moisture is 0.005 to 0.12. Rivers, lakes and inland seas are 0.14. Groundwater is 0.4 to 1.7, whereas oceans make up 97 to 97.5% of the water on the Earth's surface, and 0.001 to 0.1% is in the atmosphere. The main sources of water supply are rain. Then we have surface water. We can have impounding reservoirs. We can have rivers and streams. We can have tanks, ponds, and lakes. And in groundwater sources, we have shallow wells, deep wells, and springs. Now, what is a shallow well and what is a deep well? So, a shallow well is that which draws the water from the first level, that is above the first impervious layer. And deep well is that which draws the second level of water or deeper water. That means water which is below the first impervious layer. So the water from the deep wells, that is considered safer than the water from the shallow wells. Why? Because water from the shallow wells, it is the first level of water. It can get contaminated by the water which is discharged from various sources like the septic system, the animal houses and barns, then the fertilized fields, etc., from the grasslands and woodlands and all. So, deep water, that is below the first impervious layer, so that is safe compared to the shallow water. However, water can get contaminated even during storage. So, even safe water has to be stored correctly for it to remain safe. Then this is the supply of the water resources. So 97% of the ocean water or sea water is saline water, and 3% of water on the earth's surface is fresh water. This fresh water is divided into ice caps and glaciers, which have 68.7% of this fresh water. Then 30% of the fresh water is groundwater, 0.3% is surface water, and other sources constitute 0.9%. Now, out of this 0.3% surface water, 87% is present in lakes, 11% in swamps, and 2% in the rivers. So, if you see the utilization of ground and surface water, you will see that 89% of surface water is used for agricultural purposes, 9% for domestic, and 2% for industrial uses. And groundwater withdrawals 92% for agricultural purposes, 5% industrial, and 3% for domestic purposes. Now see, this is the map which shows us the extent of exploitation of the groundwater in the country. So heavy extraction of groundwater, especially for irrigation, has led to a fall in the water table. And this is becoming a very serious problem. So we are heading towards water scarcity, zero water cities. So 21 cities have been predicted that they will be running out of water by 2030. Chennai, it seems, is already out of water. Then we have Bengaluru, we have Coimbatore, and we have a host of other cities which are likely to run out of water by 2030. So what needs to be done? We have to catch every drop of water that is falling on the earth. And most of the rural water supply systems, they are based on groundwater sources. 85% of groundwater sources are drawn for irrigation, and rural drinking water draws hardly 3%. So groundwater development in Delhi, Haryana, Punjab and Rajasthan is more than 100%, and in Gujarat, Karnataka, Tamil Nadu and Uttar Pradesh it is more than 70%. So an imbalance is existing between over withdrawal of groundwater and the recharge of the deficit of groundwater. So this is resulting in a permanent fall in the water table every year to the tune of 2 to 3 meters. And there are three major and widely prevalent problems in the sustainable supply of drinking water. These are scarcity of drinking water, then the brackishness, then excess fluoride and arsenic content in drinking water. These are manifested primarily in areas with low rainfall and those which have high potential evaporation areas. So we have to revive the traditional methods for water conservation such as rainwater harvesting from the rooftop and ground catchment which is stored in reservoirs. So this needs to be taken up at village level in a big way. Currently only 8% of rainwater is being harvested. So this needs to be increased tremendously. Then there's a term known as water pollution. So water pollution means that something is polluting the water. That means making the water unfit for consumption. So these sources can be point source, it can be non-point source. And point source may be single large source, which can be localized to one spot like sewage pipes, leaky gas tanks, industrial sites, injection wells. Then we have non-point sources, diffuse source or many smaller point sources. Then maybe because of agriculture runoff, urban runoff, construction sites and air pollution. So we also have the flow of underground contaminations which contaminate the water table like runoff from the industries, leakage of an underground storage tank, then wastewater from the households which can contaminate the wells or it can contaminate even the rivers and the ponds. Then the classification of various sources of pollution can be agricultural, transport, it can be because of mining, industry and trade, because of public supply and other sources of pollution can be there. So these can be biological pollutants, it can be chemical pollutants, or we can have physical pollutants. So the health dimensions of water pollution are tremendous. We have various types of diseases like waterborne diseases, water-based diseases, water-related vector-borne disease, and we have water scarce or water-washed diseases due to lack of adequate water. So now there is a question that how does water clean itself? So what happens whenever a pollutant is added to a water body, then the oxygen is present in the atmosphere, it's present in the water, in the presence of sunlight, some of the organic matter that is converted to harmless things in the water body itself by dilution, by sedimentation, by small fish or animals, bacteria or molds. These digest the organic materials. But there is a certain limit to this self-cleansing by the water body. So what happens when excess of pollutants are there? Then these methods are not sufficient to clean the water body. The dissolved oxygen in water is a measure of the water quality. So if the water is gravely polluted, then parts per million of dissolved oxygen at 20 degrees centigrade will be less than 4. In heavily polluted, it is between 4 to 4.5. Between 4.5 to 6.7 is moderately polluted, and 6.7 to 8 is slightly polluted. And good quality of water is if the parts per million of dissolved oxygen at 20 degrees centigrade is 8 to 9. So why do we need to treat wastewater? Why? Because it causes a demand for the dissolved oxygen and lower dissolved oxygen levels in the streams if there is dirty water that is being added to the streams. So certain nutrients like nitrate and phosphate are present in wastewater which cause excessive growth of microorganisms. Increases the suspended solids or sediments in the stream, so the turbidity will increase. So for purifying water, we have various methods on the large scale: storage, filtration and disinfection, and then we have small scale methods for household practices. We have boiling, chemical disinfection and filtration. Now the large scale purification, the first step is storage. What happens on storage? Biological changes occur, the bacterial count decreases. The aerobic bacteria bring certain changes in the chemical quality of water, and the physical impurities they settle down. And there is a drop in the bacterial count to 90% in 5 to 7 days. Optimum period of storage of water is 10 to 14 days, beyond which the growth of organisms occurs. Then after this, in the secondary processes, the water is that is subjected to aeration and rapid mixing. Air diffuser is used. So what happens? The sludge it collects at the bottom. Then anaerobic microbiological processes take place, and the nitrates are converted to nitrogen which escapes into the atmosphere. The phosphates, if not removed in the sludge, they react with aluminium, and aluminium phosphate is deposited into the sludge. Aeration is done to strip the nitrogen gas and to reoxygenate. That means we want to increase the dissolved oxygen. So the quality of water will improve if the dissolved oxygen levels go up. In tertiary processes, there is slow mixing to keep the suspended particles and the oxygen out of this, and then we lead the effluent to a settling tank where the sludge settles on the bottom and the supernatant that is drained off. Then we have various kinds of filters. We have slow sand filters, rapid sand filters, we have pressure filters and diatomite filters. So basically, what is a slow sand filter? There is a layer of slimy growth which consists of algae, diatoms and bacteria over the filter bed. It takes some time for this layer to appear, which is known as ripening of the filter bed. And then we have the filter bed, which is made up of sand, and then we have an under drainage system which runs between the various chambers of the filter. Then we have rapid sand filters. They are different from the slow sand filters. They don't have the organic layer. In this, the chemicals are added, and by flocculation, we make the impurities settle down, and then further purification of the water will be done. So this is the table which is showing us the differences between the slow and the rapid sand filters. So this will be discussed in detail in your practical class. Then we have the next step is disinfection. So basically disinfection means we are adding a disinfectant. So what is a disinfectant? Any substance which is capable of destroying pathogenic organisms and which is less influenced by physical and chemical surroundings. It should not leave products which render the water toxic or which impart color to the water or otherwise make the water unpotable. Disinfectant should be readily available and dependable availability should be there at a reasonable cost. The residual properties should be there to prevent recontamination of water. It should be detected and be amenable to detection in small concentrations. Then chlorination of water. Chlorination is the process of adding the element chlorine to water as a method of water purification to make it fit for human consumption as drinking water. It is a supplement but not a substitute for filtration. Water which has been treated with chlorine is effective in preventing the spread of disease. So the disinfecting action of chlorine is due to hypochlorous acid and it is effective when the pH of the water is around 7. Then the chemical reactions in the water. When chlorine is added to water, it reacts to form a pH-dependent equilibrium mixture of chlorine, hypochlorous acid and hydrochloric acid. Then depending on the pH, hypochlorous acid partially dissociates into hydrogen and hypochlorite ions. In acidic solution, the major species are chlorine and hypochlorous acid, while in alkaline solution, effectively only hypochlorite ion is present. And very small concentrations of other ions of chlorine are found. The basic principles of chlorination are that the water should be free from turbidity because turbidity impedes the process of chlorination. Then we have to calculate the chlorine demand of the water. We have to have a minimum contact period which should be at least 1 hour for the chlorine to be in contact with the water so that all the bacteria and viruses are killed. So chlorine has no effect on the spores and on some viruses. Then we need a concentration of free chlorine. The recommendation is of 0.5 milligram per liter. So why? Because for any contamination which occurs afterwards, so we need to add a bit of extra chlorine. Then we have to calculate the correct dose of the chlorine. This will be the sum of the chlorine demand of the water plus the residual chlorine which we want to be there at the end of the process of chlorination. So this is just an overview of the chlorine decay, how the chlorine is reacting with the various organic compounds, the various inorganic compounds, the nitrogenous compounds, and the other radicals present in the water. So you see chlorine liquid that is converted into gas in an evaporator and it's fed into pipes and through this it is mixed with the water. So we have a term breakpoint chlorination. In this, it means that there is no ammonia or free monochloramine radicals are there in the water because ammonia is a marker of organic matter. And no free available chlorine will also be present in the water. That will be the breakpoint. And further addition of chlorine will produce free available chlorine in the water. So when we add chlorine to exceed the breakpoint, it is called breakpoint chlorination. Then we have superchlorination or shocking the system. Under certain circumstances, it will be necessary to subject the water system to an extremely high chlorine dosage. This process of superchlorination or shocking the system ensures that free chlorine residue is high enough to inactivate or destroy harmful organisms. It's usually done at the beginning of an operational season if the system operates seasonally, then after installing or repairing the system, and when the lab results indicate the presence of bacteria, then following the contamination by flood water and to control iron and sulfur bacteria. The various chlorinating agents, they are chlorine gas, chloramines and perchloron or high test hypochlorite. Other disinfectants for water are ozone, ultraviolet rays and analytes. There is a test known as orthotoluidine arsenide test or OTA test. This is used for measuring the relative amounts of total residual chlorine, the free available chlorine and the combined available chlorine in the water. So this is just a flow chart of a water treatment plant which is using rapid sand filters. So you can see that the water is mixed with alum in the mixing chamber, then it is led to a flocculation chamber, then to a sedimentation tank. Then after that it's subjected to rapid sand filtration. Then the water from the filter that is chlorinated to disinfect it further, and then it is sent to the water storage centers and from there to the public supply. Then we have small scale purification of water, which means purification of water for domestic use at home. So first thing is boiling. So rolling boil for 10 to 20 minutes kills most of the bacteria and viruses and makes the water safe for drinking. Then we have chemical disinfection with bleaching powder. We can have chlorine solution, high test hypochlorite. We can have chlorine tablets. We can have iodine liquid and potassium permanganate. And we have various types of filters. We have Pasteur Chamberlain filter. We have Katadyn filter. So what happens in filters? Different types of candles are used, like the Pasteur Chamberlain uses a porcelain candle. The Berkefeld filter uses a candle of Kieselguhr or infusorial earth. The Katadyn filter has the candle surface coated with a silver catalyst which kills the bacteria by an oligodynamic action. Then in small scale purification, we also have well disinfection because wells are also a source of water for a large proportion of the population. So how to disinfect a well? So first of all, we have to calculate the volume of water in the well in liters. So if we know the diameter of the well, we can calculate the volume of water in the well, and then we calculate the bleaching powder amount required to disinfect the well by using the Horrocks apparatus. A double pot method is used to add the bleaching powder to the well. The construction of the pot is such that it ensures proper mixing of the well water with the bleaching powder. So we have a 20-liter bucket of water and we have high test hypochlorite, chlorine granules or powder. We calculate the volume of water in the well. We fill the bucket with clear water from the well. We add 50 grams of high test hypochlorite and we stir it until it is dissolved. And for every cubic meter of water in the well, we add 10 liters of the chlorine solution. So what the importance of purification of water cannot be undermined because all types of impurities must be removed from the potable water. So safe drinking water and wholesome water, must meet with certain physical, chemical, and biological standards, and purified water can significantly reduce the morbidity and the mortality from waterborne diseases. So WHO has laid down certain criteria which are known as water standards. Now there are certain aspects of this which are acceptability aspects, which are physical and inorganic constituents. Then we have microbiological aspects, we have chemical aspects, and we have radiological aspects. So the water should be free from turbidity, it should be color free, less than 15 true color units, it should be free from taste and odor, and it should be cool. Then we have inorganic constituents. So chloride's acceptable limit is 200 milligram per liter to 600 milligram per liter. It should not be more than this. Hardness of water should not be more than 300 milligram per liter. Ammonia in water should be less than 0.2 mg per liter to 3 mg per liter. Then the pH of the water should be neutral and it should be free from H2S. Then iron should be within a certain limit, so should be sodium and should be free from sulfates. So then we have the biological aspects, in which we have bacteriological aspects, protozoal, helminths, and free living organisms. Water should be free from viruses and it should be free from organic constituents, and inorganic should be within certain limits, and radiologically also the water should be safe. So how do we do the surveillance? How do we maintain the drinking water quality? So we have to do a sanitary survey of that area. We have to do sampling of water. We have to do bacteriological surveillance. Then we have to do the biological examination and the chemical surveillance. So for sampling, we have to collect the water samples, store them and transport them for testing. We have to collect samples from taps, from rivers, streams, tanks and wells, and subject them to physical and chemical examination and bacteriological examination. Then physical standard should be there. It should be there, as I have told earlier. Standards for turbidity, color, odor and taste should be within limits. Then chemical standards should be as per norms. Hardness, chlorides, ammonia, nitrites, nitrates, adsorbed oxygen and dissolved oxygen should be within limits. Then toxic substances and a specific group of chemicals causing non-specific diseases of water should not be there. Polynuclear aromatic hydrocarbons and radioactive substances should be within limits. WHO recommends that all samples from distribution system should be free from coliform organisms. So in practice, it's very difficult to attain this standard. So the recommended standards for water samples are that throughout any year, 95% of samples of 100 ml each should not contain any coliform organisms. No sample should contain E. coli. No sample should contain more than 3 coliforms, and any 2 consecutive samples should not contain coliform organisms. In case of individual or small water supplies, such as from household tap, well, spring, etc., the coliform count should not exceed 10 per 100 ml and E. coli should be nil, because E. coli indicates fecal contamination. So E. coli should be nil. Then we have viral standards. So the WHO has fixed the limits for viruses such as enteroviruses, retroviruses, and adenoviruses in the water supplies at 1 plague forming unit. Then fecal bacteriophages and enteropathogenic viruses should be completely absent. So the bacteriological indicators are based on organisms indicative of fecal pollution. These organisms are E. coli and coliform group as a whole. We have fecal streptococci, we have Clostridium perfringens, then we have examination for protozoa, we have examination for parasitic worms and larvae, which is also recommended. So why coliform organisms are chosen as indicators of fecal pollution? Because they are constantly present in human intestine. in an average person who excretes 200 to 400 billion per day of these organisms in the feces. They are foreign to potable water supplies, easily detectable by ordinary culture methods. The survival time is much better than other organisms, and they have greater resistance to natural forces of purification. So fecal streptococci occur regularly in much smaller number than E. coli, and their presence is regarded as confirmatory evidence of recent fecal contamination of water in doubtful cases. Then Clostridium perfringens are spore-bearing organisms, and their presence along with coliforms indicates recent water contamination. The presence of spores but the absence of coliforms confirms remote contamination of water. So that's all for today. Thank you very much.